could start with questions. Pardon me. You could start with questions. Well, welcome everybody to coming back. I can see just the perfect. Not that we need. Thank you very much. Oh, good job. So this is the hardcore team, the A team. These are the guys who are really interested. Yeah, the rest of the guys, they just come, enjoy the afternoon, have lunch. You guys are the hardcore. So we have two. Good. So let me just recap what we kind of did yesterday, just in brief, and then we're going to finish up some of the material this morning, and then have some presentations, hopefully a number of them concerning geothermal, maybe minerals, groundwater issues. So the purpose of this presentation is we want to provide you with a complete spectrum of electromagnetics. I think it helps very much to see everything kind of all at once and see how they interact with each other, and also when you have a particular problem, where you might fit in. So first of all, what we did yesterday with DC resistivity, actually let me ask you, how many people had a course in which DC resistivity was presented to them? Sort of just about everybody. And in those courses, how was it presented? Was it presented in terms of currents, or did you talk a lot about the charges and that from the point of view of understanding DC resistivity? Did that ever come up? No. So that's my feeling with a lot of this, that most people teach DC resistivity methods in a way in which maybe they talk about currents, but mostly it's just, let's just compute the potentials. So you've got this differential equation, you solve it, you compute the potentials, there it is, right? But I don't actually think that gives you very much insight into what's going on physically. Whereas if you present it in terms of the fundamental aspects, which is just, okay, I'm going to put a current in the ground, and that current's going to flow. It's going to generate charges wherever there's a change in the electrical conductivity, and it's those charges that generate those electric fields or voltages. I think you get a much deeper understanding about what is going on. The other thing that comes into play in that is that it helped by thinking about the charge accumulation. It helps you come to grips with, am I exciting the body? So because you need to establish some charges on something in order to have a field that you can measure. So thinking about the charges is very important also from the point of exciting. And then the other aspect has to do with measurement of the data. And once you understand the charges, once you just sort of visually see the charges, then okay, now I know I somehow want to be there. And then the other aspect of okay, well, sometimes I actually get an overshoot. I get a number that's different from any number that is in the model. I don't think you can explain that very easily just by solving your differential equation and just getting the voltages out. I mean, then it's just kind of an answer like, okay, but you don't have any understanding about where that comes from. So I think there's a lot of information and insight that comes about by talking about the DC resistivity problem right from scratch and just thinking about the fundamentals with respect to charges. We then went on to the EM fundamentals. There was both Ampere's law that showed the relationship between a current and a resultant magnetic field. And then there was Faraday's law that said if I have a time varying flux at some location, that's going to give rise to an electric field. And there's two aspects with respect to that. One is that if I've got a loop here in which I have a time varying current, then that actually changes. There's a time varying flux everywhere. Okay, so that means that there's an electric field everywhere. That's the first step. The second step is that if at some point where there's an electric field, there is also significant conductivity, then I will set up currents in that position. Once I have those currents, those give rise to other magnetic fields that I can measure elsewhere. But again, thinking about things in terms of those two-part systems where you first establish an electric field, and then if there's conductivity, you get currents, and then you've got some information about the subsurface. Thinking about that then really allows you to understand. So your name again is that? Ariel. I was going to say that, but I was like, I'm not sure. And you are?
Daniela.
Daniela. Okay. So if Daniela is a conductor and Ariel is a resistor, I make a change of magnetic flux here. So there's an electric field there, right? But you're a resistor, so there's no currents that are built up in you. You're a conductor, so you get lots of current. And so that really promotes that understanding of why electromagnetic induction, you can see conductors, but you don't really see resistors. And that's a really important thing to take through because it just crops up in everything that you want to do later. Actually, one of the things that we found in the DC resistivity was that you might have a, if your object is just buried in a nice background, you can see it, but if there is a thin resistive layer over top, you can block the currents from coming through, and so that can mask your object. If you have a conductor, you'll mask also this object. That was the motivation for doing the inductive sources, where now you can see conductors. If there's a thin resistive layer, there's no problem. The EM fields just travel right through. If there is a conductor, then currents get induced into that conductor, and you're still can be kind of blind. So from there we went to grounded sources, and that was interesting because we had grounded sources because now we have the aspects of the DC resistivity problem where you're putting through the currents through the ground, and you also had the inductive parts that's coming from a wire. And we actually saw that a wire is really important. And where you have the wire, if you're going to do a field experiment, where you lay out that wire is going to be pretty important if you're going to do a time domain experiment or do some kind of inductive experiment. So we're going to come back to that a little bit later because we're going to do IP. And we're going to see that there's a lot of electromagnetic induction effects from that wire. Grounded sources form the basis for many experiments. In fact, that's the fundamental aspect for all of the marine EM problems, but there's also lots of land problems that you can work with. And in fact, in DC resistivity, of course, you use grounded sources, so it'd be a matter of just putting in a time varying current in here, or doing a step off and measuring the signals early in time that actually kind of connect these two guys. When you have large scale problems, volcanoes, big porphyry systems, base of the salt, the basic issue is energy, and you need to get energy into the ground. And for that, we just don't have in many. Sometimes you can build a big loop, and certainly that's done quite a bit. They'll make a loop a couple of kilometers on a side. It's still a lot of wire to lay out, but it can be done. The other aspect is that you can appeal to natural sources. Most of that energy comes either from lightning strikes, and we saw that the Earth is kind of like as a waveguide. There's the conductive Earth and the conductive ionosphere, and then the waves just sort of travel around through them, as well as these solar storms that come in. So that's about where we got to yesterday. What I want to do today is to finish up. So we're going to do ground penetrating radar. We're going to do IP, and then just talk briefly about the future. So I think that'll probably take us probably into coffee or maybe beyond. We'll kind of see how that goes. And then from there, we'd like to switch over and have you talk about some problems that you're doing, since you spent all night putting slides together and you're excited about telling us what you're doing. So, okay. Just like, okay. Anyway, so we want to listen to what you're doing. And then after that, we'll talk about SIMPEG. Lindsay will take you through our site, GeoSci, talk about SIMPEG, and show you some of the tutorials that we've got, and just use that as a basis for extended communication and development. So that's sort of the plan. Any questions? So, okay, I have one question. So last night, okay, when you're tucked away in bed, who dreamt about charges? Who dreamt about currents? Nobody? I'm so disappointed. Okay.
Seriously, at least one. Do you want me to get these lights? Is that too bright, or is that okay? So that's fine.
Oh, whoopsie. Okay, who's been involved somehow in a GPR experiment, ground penetrating radar? And what was the circumstance?
Now, our company is performing a device to detect crushable elements inside the shards of the kites, the truck, mining truck. Our idea is use the GPR, some support structure, and the kites pass below this structure. We take the data GPR. We want to view the response in the radar grams associated to uncrushable elements.
So what do you look? I missed it. What are you looking for?
Uncrushable.
Metal pieces.
Metal pieces.
Yes.
I see. Oh, and you're doing that with the GPR. Oh, interesting. No, but they're not using GPR. They're using EM. So we've seen cases where they're using EM sensors because I guess the teeth of these great big bulldozers or whatever they're using to dig up the ground, is they were digging this stuff up and then stockpiling it. And occasionally there'd be these teeth that were left inside, and then they're going to take this material, bring it back into the mill, and if one of those things gets in, causes havoc. But that was done from the point of view of using an electromagnetic method that's then responsive to both conductivity and to permeability. But you're actually using it for GPR. That's interesting. All right, got it. Okay. So what's the motivation for GPR? Basically, it's smaller scale structures in general. Maybe sinkholes, saltwater intrusions, it has been used. Here's a big application. It's just in engineering types of problems, looking for buried tanks, looking for buried wires, anything that's metallic, used in archaeology, and it's also used in glacier models and glacier studies because GPR travels really nicely through ice. So we're going to look at the basic experiment, talk about some physics, some field examples, and a bit of a case history. So here's the experiment, and for how many people here are seismologists? There was a few.
Long time ago.
Long time. So the one thing about presenting this, there's often a number of seismologists that are just trying to figure out, okay, what the heck this electromagnetic stuff is. And then you show them GPR and they're just so comfortable at home. And the reason for that is that the whole scenario is basically the same as in reflection seismic. You have a transmitter, energy goes down, reflects back up, and because you're talking about wave phenomena, the difference here is that this is an electromagnetic transmitter, and here's an electromagnetic receiver, and the information that's going down are just EM signals. They're not acoustic signals. So now we got Maxwell's equations. We showed these a couple of times yesterday, and the term that we had been getting rid of was this guy here. But this D is called the electric displacement, and if it varies as a function of time, then that's also going to give rise to, that's effectively a current, and that's going to give rise to a magnetic field. So this was the conduction current, the sigma E, that's Ohm's law, and this is just another current called displacement current that can arise. So if we take the first order equations and we combine them into a second order equation that looks like this. This term we had left out before. Today, this is the term that is going to be not only left in, but is actually going to become dominant as the frequency gets higher. Yeah.
Not quasi-static.
Pardon me? I'm sorry?
GPR is not quasi-static?
No. No. when you say quasi-static, you're basically saying that this term is much less than this, and then you get rid of it. The physical property that's of interest is the electrical permittivity. And usually we take the ratio of the permittivity of something to free space, and that gives us a relative epsilon. And that's often referred to as the dielectric constant. Air, of course, has dielectric constant 1. Fresh water is 80, salt water is 80. Ice is very low, maybe 3 to 4. And other materials have different values. One of the important things is that a GPR wave is going to travel in the Earth at the speed of light divided by the square root of the dielectric constant, epsilon. So if epsilon is equal to 4, then this wave is traveling at half the speed of light. Okay? We have to worry about attenuation, skin depth. So on this axis, we've got skin depth. On this axis, we've got frequency. Where we were yesterday, we had this skin depth, this particular skin depth formula. That was for the kind of that quasi-static. So basically, it told us the skin depth varied as square root of frequency. And we were sort of in this region in here. These are frequencies, that's 10 to the 6th hertz, that's 10 to the 9th. So we're getting up to really high frequencies here, so that's gigahertz. Notice that the attenuation sort of has this sort of form, and then there's a region in here where things start to change. So this is where that wave part of the system starts to kick in, and then by here, then the attenuation is looking like that. So you don't have that extreme decay. It actually propagates kind of as a wave without losing so much energy. So that's a very big difference than the diffusive waves. And here's what the skin depth looks like if you have if you're sort of on this in this area. So again, we can come back to try to see how things look like. What happens if you put an electric dipole in a hole space? We did that yesterday. That was a fundamental, and we put an electric dipole in a hole space, and we used that to see, then we turned it off and we watched how the fields diffuse. If you have an electric dipole in the frequency domain at 10 to the 5th hertz, this is what the field lines look like. And at 10 to the 6th, this is what the electric fields look like. So notice the complexity of the structure here. So these, and the changes of the sign. So these electric field lines are going like this, and then these ones are going in the opposite direction. When you look at 10 to the 6th hertz, notice how frequently they're changing. If you actually did a line across here and you plotted what the electric field is, you see it's down here, it's up here, it's down here, it's up, down, up. So it would almost look like a wave. And you could compute what the wavelength of that is, and you'd find that it is in fact the velocity of this medium divided by the frequency. So this kind of nice physics to run and interact with. So how does all this behave? What we're going to do is to set off a radar pulse and then watch how that pulse travels. And there's going to be energy that's going to go out. So this is air, and this is a layer. So it's got one dielectric constant. This is going to. So these are the wave fronts. I explode this, and this is kind of my wavelet, there's a positive and a negative, and then a positive. So it's like a seismic wave, you know, it's got some structure to it. And that wavefront is moving out. There's a wavefront that's moving down in, and this is going to interact with this boundary, and you're going to get some type of reflection. Okay, so you can see it reflect. In the end, here's your ray path. So this is one that's going down. This was that prime wave up in here, and so these different wave fronts here correspond to different rays here, and so that we'll see how the energy travels. So what about the processing? So first of all, think about the frequency that we're doing. So we're working at high frequencies, maybe 100 megahertz, right? So that's 10 to the 8th hertz, or if you look at a period, it's 1 over that, so that's 10 to the minus 8 seconds, or 10 nanoseconds. You set that pulse off, okay, and there might be some amount that's reflected from aerial, some next row. You know, so there's going to be a certain time for the information to kind of go through and come back, and then eventually, I don't know, right? But that time might be maybe 200 nanoseconds or something like that. Now, what that allows you to do is, even if you're pulling an instrument along, okay, you have ample opportunity to send multiple, you know, send a pulse out, get a record back. Send another pulse out, get another, you know, dot. I mean, you could do this hundreds or thousands of times in milliseconds. So what that means is that you can take an advantage of stacking. So we're not only going to send one pulse out and get a record back. We're going to do this again and again and again and again, and then we're going to take, you know, here's a trace. Now we take 5 traces and we stack them up. So now we do 20 traces, stack them up, and get something like that. So again, this is you know, similar to what's done in a lot of problems where you just do repeat measurements to gradually build and stack them up, average, to get rid of the noise. There's geometric decay of the information as it's going out. There's spreading. And so what you want to do is to take that into account, and you can do that with applying some kind of a gain. Again, this is what's done in seismology. There's always a gain function that's applied. Do that, and now you end up with a signal that maybe looks like that. So now you've got these guys here. There's your wave, and there's a positive event, and then there's a reflection, different polarity, and you've got this kind of. So that's what you want to use for your radar gram signal, and then you're going to put them all together and see what you get. So what we're looking at here is a cylinder, a sphere, and we've got a radar unit, both a transmitter and receiver, that is going to get pulled along here, but at this particular time, it is going to explode here, and then there's going to be information that comes down to our reflector and then comes back out. So we're going to look at the wavefronts. Now the wavefront's going down. So now you can see it interacting. It's coming back up. If you're sitting at the surface, so if you're sitting over here and you're recording what you see, then, you know, there's going to be nothing, and then there's going to be there's going to be that reflection that comes back in, and then nothing. Right? So you're sitting over here, there's going to be a two-way travel time to get there. As you come back over here, the travel time gets less because your distance is less. And so that would correspond to a radargram that's sitting right here. As you're pulling this transmitter receiver over top of that, you end up then with a kind of a reflection hyperbola, just the same as in seismic, that looks like that. So this is your information about your scattered object. We can use that for a couple things. One is if the object is going to be directly underneath where the apex is here. And then this parabola, that depends upon what the velocity of the wave is in here. So we can actually get the velocity of the wave, we know where it is, and we could actually convert this to depth. Notice that, again, for people who are interested looking at seismogram, this looks like a regular seismogram. The thing that's a clue that this might not be is that that's in nanoseconds. So it's not in, usually, this would be a particularly good scale for seismic if you were in milliseconds, right? But this is in nanoseconds. So what do radargrams look like? Well, here's an example. Here's some buried tanks. And you just go over and you see images of them. This is why GPR is so easily adopted, is because you get an image, you just plot the data, and you can see what your geology is. You can see what your engineering problem. So here's the location tank. You can see there's 1, 2, 3, 4. And then there's also additional reflectors that are coming in here, so there's something. And these tanks are sitting on beds, so that allows them to, you're actually seeing the tank bed as well as the tank. The GPR system comes in a whole variety of configurations and sizes. The size of the unit is inversely proportional to the frequency of the system. So if you have a 50 megahertz antenna, it actually might be fairly big, might be a couple of meters. If you have a gigahertz antenna, you might put the whole thing in a box. So the guy's here is probably operating at around a gigahertz. So he's just looking for wires and things inside a foundation. So he's got a mat over here. It's all plugged into a screen. He's just moving this GPR system, which is both the transmitter and receiver, back and forth across here, getting the radargrams, seeing picture. Sometimes, in archaeology, here's an example. The unit is sitting here, and he's just pulling it. Sometimes you have the antennas that are independent of each other, and you can do various things. You can change orientations. You can move them away. These antennas, you could imagine doing excuse me, a common midpoint together. You simply take a midpoint, and then you gradually expand the transmitter and the receiver symmetrically about that point. And then you could think about these reflections that are coming from a single point. Or you have a common offset where the transmitter and receiver are just all in one little buggy, and you just move that along. So those are different acquisition systems, again, very similar to what you'd see in seismic. Just a couple things here with respect to the use of it. This was actually something that was done up at UBC. We're interested in lithologies and water content. Actually, there was a region here that GPR line was acquired. It looked like this. So here's so here is GPR. There are reflection events, so there's probably a layer boundary associated with this, and then not really sure what happens. Maybe it kind of dips off a bit or something. But an important thing, excuse me, here is that there's a region where you just kind of lose information. Over here we see deep. Over here we see shallow. So why is that? In that attenuation plot that I showed you, the skin depth, the depth of penetration also depended upon the conductivity. So it was independent of frequency, but it did depend on conductivity. And if if you had a higher conductivity in some region here, that might explain why you're no longer getting energy through there. So we did a DC resistivity experiment over top and inverted that. So this is depth as a function of distance. And you can see that there's a sort of a high conductivity layer that's coming in here. And so that's really what's masking this. So conductivity plays a crucial role in GPR experiments. If you've got a GPR system and you're trying to use it on resistive ground, you can probably see deep. If you're using it on conductive ground, you can't see. If you put it on the surface of seawater, for instance, you might only get a quarter of a centimeter in to the water. Here is the example of underground storage tanks. You kind of saw that before. And you can do the processing so that you end up with kind of like a 3D radiogram. And then you can do horizontal images, sort of time slices or depth slices if it's converted to depth. And you can see the tanks, and then at some point you can see the tank beds. This was an example for mapping peat thickness. So you've got the radar unit here. You go along and get your radargram. There's topography on there, so you do a topographic correction. You end up there's a reflecting event that's coming in here, and this is the thickness of your peat. This is Ireland. They're actually still interested in peat. They're still burning this up. And here's a way of quickly getting some information about that. So this is tremendously fast, right? You're just driving this thing over.
We don't know what peat means.
Oh, peat? It's sort of partially decomposed organic material. Right? So you burn it, right? Subsurface utility mapping. So here, the GPR is sensitive. You get a reflection both from anything that changes a dielectric constant. So if you had a PVC pipe, okay, that was there, you'd probably get a reflection events from this plastic pipe. Okay. If you had a metallic pipe, say an iron pipe, you would also get a reflection. So it's your reflectivity depends both upon the conductivity and the electrical permittivity, the dielectric constant. So that's what's happening here. We've got a water pipe that's iron, and we've got a gas pipe that's just plastic, PVC. So they want to find both of them. And they make a grid, go over top, get the GPR sections, and then do horizontal plan view sections at particular depth. And then you can see here, this is the plastic pipe up here, and this is the iron water pipe down there. So they're displaced horizontally, and you see them. So this is great. You get circumstances like this, and it's kind of like a no-brainer. You just go along, you collect the data, and what you see is a direct reflection of what's there. It's used a lot in mining applications. The big issue there is water. Water's got a very large dielectric constant, so it makes it an ideal kind of target to use. This is work that was done in Saskatchewan. It's a potash mine, and yeah, water kind of comes in. So these things are about 1 kilometer under the ground, and they're actually immense. The first time I realized how big they were, but there's like, I don't know, it's like 2,000 kilometers of mine underneath Saskatchewan at 1 kilometer down, right? It's just immense workings that are there. Anyway, they get, there's layers of water above you, and you're mining this stuff out, and at some point something might crack through, and first thing you know, you've got water like that. So you want to be able to see, okay, where is the water above you? So you can take a unit, GPR unit, and you just put it up on the ceiling, right? And now you're doing, you're doing a GPR experiment, but you're actually looking up this way, which is what they're doing here. So it's logistically more difficult, of course, but still you go across and get a GPR radar ground and then see what you got. An application that we just recently kind of discovered, but I think this is one that really tweaked my imagination, because first of all, it's something that's useful potentially if it can really work, and secondly, it's a conduit for opening up a conversation with the public about the use of geophysics, about the use of looking underneath the ground. And it's something that's kind of tangible, and once you could use this as a little widget, a little way to kind of start communicating with people about, okay, we have a sensor here, and we're going to look under the ground and get some information, and this would be an application to driverless vehicles, but once you've done that, then it's like, okay, well, maybe we're going to look for groundwater, or maybe we're going to look for something else, but it just sort of opens up that conversation. And that's why I think this was particularly interesting. So what's the idea here? We've got typical sensors. If you want to have a driverless car, it needs lots of information. And most of that is now coming from optical sensors, GPS, and these things are great. They work fine in good weather. But like, what happens if there's bad weather? Rain, snow, sleet, fog, whatever. And the optical sensors are not collecting the data that you'd like. And so you need another sensor. So here's a possibility. You take a GPR unit, actually you take many GPR units, and mount them underneath some vehicle. And then that GPR signal goes down, and then you drive over some region on a clear day, and you just collect a reference data map for what it's like if you're driving this unit over this particular road. So you get a reference data set. And when things get bad, can't see outside, you still go over with your vehicle, you get now a radar set. And now you want to do a cross correlation and correlate this with the reference data set and find out where these things best match. So in this particular case, the reference data set and the active data set, there's a best correlation that's happening right here, which says that you're 2 meters east and 0 north. So that's the idea. The concept is simple. The practicalities are that you want to be able to, you're driving the car, right? So I guess if you're in downtown Santiago, it doesn't matter. Like about 1 kilometer per hour is fine. But if you're on any sort of reasonable road, you want to do like 60 miles an hour, and you still want to have good accuracy. The example that I'm going to show you is actually one in which they're driving along on a snowy road, 60 miles an hour, so that's like 100 kilometers an hour, and they're getting 4 centimeter inline accuracy as they're doing that. So And especially if you started to, get a lot of cars equipped with these units, I mean, you just gradually build up your reference data sets, and every road would be mapped out, and it could come, right? And so it'd just be really interesting to see what happens. Yes.
Maybe walking for blind people.
Ah, yeah, that's actually good. Yeah, that's a good idea. I'm gonna go to the patent office. You take a while. I'll be back in about 2 hours. Yeah. Yeah, so if you have.
Just put my name on that, I don't need the money.
Oh, it was, yeah, your name, was it Doug? Well, yeah. Okay. Let's see. We don't have an example, and this is not quite one of the places that might be of importance in Chile, and we do not have an actual example of this, but the dielectric constant of ice is very low, like 3, something like that, 3. And so that distinguishes, so the radar waves can actually travel really through long distances of ice, and then they can reflect back. What that does is open up the opportunity for using airborne GPR to estimate the thickness of ice. In places where you're interested in, okay, how fast are the glaciers receding, or how much fresh water do we have stored in the ice? How is it changing as a function of time? The airborne GPR offers a very, very good way of trying to get that information. So that's being flown a lot in various places, and we'll probably see more and more of that, especially as the warming climate is definitely eroding the glaciers, and you just want to see how bad that effect is. We have a case history on rock glaciers. This, I don't know whether that's particularly germane here. I'll just mention what the case history was and the outcome that was obtained. So this is in Switzerland, and what they're concerned about is they often have glaciers. Doesn't look like a glacier, but there's a lot of ice and rock. It's just all kind of mixed up, right? And there's some questions about how these things flow, and there's concerns about how unstable they are, because they could just sweep down and wipe out a village. The object here was then to use ground penetrating radar to see if you could determine what the thickness of these units were, or if there was sort of multiple strata that actually define the rock glacier. They're more complicated than just an ice glacier. The bottom line is they did some work. Let's see where I have this. So they did some work with ground-based GPR systems. So he's pulling this stuff along. It's in the wintertime now, so there actually is snow. And they looked at the seismic, or they looked at the GPR sections, and they couldn't make any sense out of it. It was just noise. So then what they did is they said, well, maybe we should mount the GPR system on a helicopter and take it up. And the reason for that is that the noise was not really random noise. It was true signal that was coming, but the structure is so complicated that you just couldn't see it. You just had reflections from everywhere, right? So in fact, what it means is like, wait a minute, I'm actually getting too much resolution, I'm getting too much signal, and I can't understand anything, right? So that actually happens in kind of a number of cases in life, right? Lindsay and I were walking through a museum. Where was that?
Mexico City.
Mexico City, that's right. So we're walking through this museum in Mexico City, and there's these great big wall murals, right, that we're on, right? And we're walking, so it's there, and we're walking by there, and we're like, just trying to figure out, okay, what is this, right? And you try to kind of see things, right? But it's just really hard. And then we walked around, and then we're on the other side of the corridor, so that now we're way far away, and we look at this thing, and now we can see the whole thing. And so our resolution is poorer, but the information content that we're getting back about what's there was like night and day. It's like, oh my God, that's what it was, right? And so it's an interesting picture. But it sometimes, usually we say, oh, you want to be as close to the object as possible to get the best image. And generally that's a pretty good rule of thumb, but sometimes if things are complicated, you just have too much information, and so you need to step back a bit. And that's what they did here. So they stepped back, they flew the helicopter up, I don't know, 20 meters or something like that above the surface. So it's poor resolution, but suddenly the whole picture now starts to come into play, because all of these small scatterers, that information is all falling off geometrically, and at some point you just start to have the whole picture emerge. So that's kind of interesting. I think that's an important lesson from this case history, as well as just understanding a little bit more how the GPR works. But certainly from Chile's perspective, the thought about using GPR to find ice thickness may be something that's very worthwhile pursuing. Okay. Okay, we're now going to go image polarization. Just a show of hands, how many people have been involved in an IP survey? Few. How many people have never heard about induced polarization? Traditionally, what we've been referring to up to this point is that the resistivity, a rock has a particular resistivity. So I take a chunk of rock, I put it in a little device, I put a voltage across it, and I measure a current. Okay? With that current, I can get, I can use the voltage divided by I get the resistance, and that allows me to get the resistivity. That measurement is usually done at a particular frequency. What is then found is that if I change the frequency, I actually get out a different number. And not only that, if I actually looked at the current, okay, there would be a little bit of a phase shift between the peak of the current and the peak of the voltage. So just the same as we did in the fundamentals of EM. Remember, we had a primary current, and a secondary current. There was a little bit of a phase shift. Now that phase shift is not caused by EM induction. It's caused by something else. But because we have that phase shift, then we can divide things into like a real and an imaginary part, right? And what we find is that the electrical resistivity of a rock depends upon frequency. So the higher the frequency, the lower the resistivity. And that there's a real and imaginary part. All of that comes about because of that mutation. Okay? So that's interesting, right? So a rock doesn't have a necessarily a specific value for resistivity, but it depends upon what frequency you're talking about as far as that rock goes. And that might actually have some important ramifications. So we often refer to this as the physical property being dispersive. So if it has a frequency dependence, then we say it's dispersive. So applications are minerals, permafrost, groundwater, acid sulfides, and maybe geotechnical, and a whole host of things. So as people are starting to learn more and more about IP and to understand the mechanisms, the applications are increasing. So I think you're going to see a lot more work that's being done in IP and actually looking at dispersive aspects of magnetic permeability also. I just want to get into your minds a concept model. That's important. You need to have a concept model, or at least it greatly helps, because then you always have a way of kind of transferring things. Like something's happening and you have a concept model and it's like, oh, okay, I kind of get it. But here's what happens. Up until now, when we've been doing DC resistivity, we have a current source that might look like this, and we measure voltage that kind of have the same shape. If we have a chargeable material, or if the material that we've got is dispersive, I'll show you in a sec why we call it chargeable. If we have that dispersive material, I have a current that goes on like this. But the voltage, when I turn the current on, initially rises, and instead of stopping, it just keeps rising up. It keeps going up. It's like an over voltage. It's more voltage than you would expect. Now I turn it off, drops down, and then it decays. This phenomena was first discovered, I think, from a geophysical perspective, right after the Second World War, early 1950s. And initially they couldn't understand what it was, and they just referred to it as overvoltage. We now understand that it's a microscopic phenomenon that depends upon pore spaces, fluids, and stuff like this, but it actually has macroscopic manifestations. So we see it macroscopically, but everything that's going on is just connected with what's going on at a microscopic level, and a lot has to do with surface area to volume area and to existence of clay particles and stuff like that. So you need a way to think about it. There's actually quite a few mechanisms by which the electrical conductivity can vary with frequency. So there's no one single one. The one I'm going to show you is something which we'll refer to as membrane polarization. And here's a way of kind of conceptualizing it. So let's suppose that we initially, so now we're imagining two grains of sand here, and there's a bit of a connection. There's a bit of a pore throat. At equilibrium, all the charges are just distributed like that, so there's equal positive and negative charges everywhere. If we apply an electric field to this, so it's like an electric force that's coming up here. It's just kind of like, imagine a battery. So we put the positive end here and the negative end here. So that applies an electric field across this way. So the positive charges are going to try to go away this way. The negative charges are going to try to go this way. If there's a blockage up here, then these particles can't all get through, and they're going to kind of build up, and they'll build up until there's a certain number here, after a while, I can't put in another positive charge in here because these positive charges are going to actually repel that, right? So you can see where you might gradually get an asymptote. So that might be an end product, and then if I look at that end product, and I just look at the charges, I go, oh, I got like an excess of positive charges here and an excess of negative charges there. And what is that? That's like an electric dipole. So that's where the word polarization comes in. So it's electric polarization. And it's induced because you're putting current on it. So that's where induced polarization comes from. So that's a good way of kind of thinking about it. As I said, it's a cartoon. I mean, it's not an entirely ridiculous physical model. There are cases where that actually happens, but there's a lot of other ways of building this up. But whatever, all of these things have the following kind of consequence. You start at equilibrium, you do something, and then there's a buildup of charge, and that asymptotes out to some value, and the region is left with some electric polarization. Okay, and of course, once we have that, then if we were measuring the electric potential at the surface, we'd notice that. So this is just another set of charges that are going to give rise to the potential. What's chargeable? Well, we've got minerals, pyrite, big guy, graphites, chargeable. From materials, sulfides are really the big kid on the block. They've got very large chargeabilities, and other rocks are in between. Let's go back to our cartoon model. The moment that we turn the current on, there's a rise in the voltage, and then as these charges build up, initially it's pretty easy to put in extra charges here, right? So that's why initially it kind of builds up quickly, and then later on it's just more and more difficult, and at some point it just asymptotes out. We can't put any more charges in there, so now you've reached a steady state. Turn the current off, and instantly the DC potential drops, so that goes down. And then now you've got all these charges that are sitting there, but there's no force keeping them, so they're just going to distribute back. And so they're going to decay initially quite rapidly, and then decay like that. So we can understand this voltage in terms of this process. And I think that's really all you need to know to have that physical connection. You also recognize that anything that you measure about this guy is going to be connected somehow with this chargeable body, right? So that this signal here is all due to those polarization charges. So anything that you measure here, it could be a value of this potential at a particular time. It could be an integral of this potential. It could be anything that's associated with it. It's a valid number to say, this is going to be my my measurement value. Theoretically, and this was introduced by Siegel, the concept of chargeability is encapsulated in this quantity eta, and that varies between 0 and 1. And for many materials that we're concerned with, eta is actually a fairly small number, like 0.1, something like that. So its net effect is that if a material is not chargeable, its electrical conductivity is sigma. If it is chargeable, its conductivity is altered slightly to 1 minus eta. So if eta was 0.1, then the fact that it's chargeable means that the conductivity is only 0.9 of what it would have been without being chargeable. Theoretically, the real chargeability data would be the ratio of phi s here. That's the maximum value of a secondary potential divided by this primary potential, phi s over phi eta. If we could do that, that would give us the value of eta. However, we can't measure that, so we're going to have to measure something else. And as I said, we could measure, let's say, a value at a particular time or the integral of that curve, either one is fine. We can also do the same thing in the frequency domain. So now we're putting in a source current that looks like this, so it's harmonic. And now we get a measured potential that, again, it's got a phase shift in it. So this phase shift is not due to EM, that's a whole different process. We're assuming there's no EM effects here. But that phase shift is due to the buildup of those charges. And so if we measure that phase shift, we've got something that's connected with those charges that are being built up. So that's a valid number. And that's then usually in terms of milligrade. So how do we work with IP data? Well, we recognize that if something is chargeable, it's kind of perturbing the conductivity a little bit. It's changing. So I had chargeability of 0.1. That meant that the conductivity was only 90% of what it was. So it's a perturbation. So we can use that idea. So we could write any IP data as being kind of a perturbation, or, well, it's a sensitivity, if we like, times an apparent chargeability. So this apparent chargeability we have here is going to be the same units as our IP data. So what we're looking at is that the IP data that we measured, maybe it's in milliradians, milliseconds, millivolts per volt, whatever, is going to be related to a pseudo chargeability with the same units times this matrix J. The matrix J is really a sensitivity that's obtained from a DC resistivity problem that would show how a change in the conductivity relates to a change in the data. Right, so chargeability alters the conductivity a bit. If I alter the conductivity a bit, then it's really the sensitivity matrix that tells me how that would affect the data. Does that make sense? Okay, so that's the idea. So I want to see what the effect of changing the conductivity is by a little bit for each element here. That means that I just need to compute that sensitivity. And I'd be doing that in the DC resistivity problem, because there I've got a conductivity, I want to change the conductivity a little bit so I fit the data. So now we're kind of using that same mapping, and then I use that as my mapping. So that means that I can write any IP data as a matrix vector product, where this matrix here is a sensitivity matrix, and this eta here is a pseudo chargeability that's got the same units as this. Okay? Yep. Yes. No? Yeah. Okay. So just to summarize, so we could do both data in the time and frequency. We could write it like that. That's great, because this is a linear problem. It's like gravity. It's like magnetics. It's like crosswell tomography with straight rays. So let's look to see now what we get. So DC and IP data are taken at the same time. Same instruments. We're just measuring at a slightly different time. So we can plot them up in the same way. There's no reason we can't plot them as data and pseudosections. Here's a chargeable block. So now the conductivity is completely uniform. The only thing that's changing is the chargeability. So we got a chargeable block here. And the pseudosection from that, so the observed apparent chargeability, kind of looks like this. So again, it's similar to what we showed with the resistivity, right? You got these kind of things with Pantlays. But remember, this is just a plot of the data. And we shouldn't be interpreting this geologically, but if you did a drill hole here, you'd have been successful. Not right through here. However, just the same as in the DC resistivity, if I start to put little chunks of graphite or clays or something like that up here, now my pseudosection looks like that. So again, completely mucked. You cannot make any interpretation from this guy at all. And similarly for this model here. So again, all of these guys have just a single conductivity. Conductivity is not altered. Only these blocks are chargeable. And so here's our pseudosection. And again, if you drove on here, you drove through there. So exactly the same. So we need to invert the data. And here's how we're going to do it. We're first going to go out and we're going to collect the DC and IP data together, right? So we're going to put in, a square wave, turn it off, okay? And we're going to measure in the off time. That's going to be the IP signal. And we've got the DC data. So we're going to take the DC data first and invert those potentials and get a conductivity structure. So here's your DC resistivity problem. Remember I said in order to understand IP, we have to have the sensitivity function. So we're going to use this conductivity, compute the sensitivity, and that gives us more of that modeling mapping. So that gives us that matrix J. Now we're going to take the IP data and we're going to invert for the chargeability. Okay, so it's almost like two distinct physical properties at this point. We've got a conductivity model, and we've got a chargeability model. This is actually a field data set. It's one of the first ones that was inverted in for mineral deposits. It was way back in, I don't know, 92, I guess it was. This is a Century deposit in Australia. Of interest were these regions in here. Those were the mineralized zones. And you can see that the electrical conductivity, it's sensitive to the overburden, but not doing very much else. The IP, however, the chargeability, produces this. So we've got strong chargeabilities here and here. So it's actually even kind of delineated these fault regions in here. So that's really nice. And it shows you something else that if you're looking, well, for various things, but in this case, a mineral deposit, the conductivity and the chargeability don't necessarily need to be aligned. The conductivity may not tell you very much, and the information is in the chargeability, or could maybe be vice versa. So now let's look at our inversion examples for a single prism. Here's your pseudosection. There's the recovered chargeability. So that's great, right? So we've got this guy completely sort of localized. And here, where we had mucked data, we recover this. So we not only have the body, but again, we've got some manifestation. Like here's some of those chargeable bodies. So they might just be surface graphites or clays. Yeah?
In the other picture, for that one, that is the model forward, no?
Yeah, so this is the forward model data. So that's the,
and that one is the inversion?
that's the predicted data. And this is the inverted model, and this is the predicted data from.
But the colors or the values is different recovered, and the bottom is that one is because it's the same in DC, because the value of that chargeability model is 10 for that.
Right. Yeah.
And the other one is the 7.
A 7. Yeah.
Is the same in DC?
Very often, actually, especially when you're asking for kind of smooth inversions, then you're going to take that physical property and you're going to distribute it out. So this value here of 0.7 is the maximum. You can see it's sort of distributed outward. Yet if I do a forward modeling of that, I get this, which actually is a pretty good match to that, considering these are data with errors on it. So very often your inversion results will have a lower amplitude than the true values if you are working with smooth models and if you haven't sort of overfit the data. Yeah, you find that too in if you do gravity inversion or magnetics inversion, and you do a synthetic and you make an object with a particular density or magnetic susceptibility, and then you go ahead and invert with smooth model inversion, the amplitude of your recovered anomaly will generally be less. The image might look pretty similar, but the amplitude is really high. Nevertheless, forward model those, and you still fit the data. That was a good point. For what it's worth, it's kind of interesting, maybe. If we look at this example here, okay, yeah, so we're now seeing these guys here. Notice that the scale has actually gone up because we've got some higher values here that are closer to 10 milliradians, and that's more of a reflection of what's there. And if we go to this GIF model, that was the pseudo-section. Here's the inversion result, and there we go. So that's all very much kind of in parallel to what we had with the DC resistivity. So let's now go back to this case history that we looked at right at the beginning. So if you remember, our initial question was, can we find a mineralized zone in these background siltstones? There's some volcanic units in here, and there was this breakaway shale at really high conductivity. We're now going to change the question. So our question is now, can a conductive and chargeable unit, that would be a potential target, can we find that in these siltstones? So now we need to look at both physical properties. So we have conductivity and we have chargeability. In the conductivity, the Mount Novot horizon, which is what we're interested in, had a high conductivity, certainly much higher than the volcanics and higher than siltstone, but was less than the breakaway shales. So it kind of stood out, but not 100%. If we look at the chargeability, however, we see that no unit outside here, the volcanics, even the breakaway shale, has got a significant chargeability. So only the Mount Novot horizon has a high chargeability. So that is going to be the thing that should be really diagnostic here. So just to remind you where we were from the DC resistivity, we had done the 3D DC resistivity inversion. We found this great big conductor in here that was that black shale, and there was a moderate conductor that was coming in here. So our survey and data are the same as they were before. We've got pole-dipole experiment. Here's the pseudo sections that we've got. So remember the lines. So the geology was running kind of north-south. They did 10 lines of data, and in the DC resistivity, we put a current here and then measured the potentials. Then we also did a current here and measured the potential. So we excited it from two ways, doing the same thing here. The pseudo sections look like this. And you can see there's definitely something there. So this is chargeability sections here. And now what we're going to see is a 3D chargeability model. So in order to do that, okay, so we've taken this 3D, we do the 3D DC resistivity problem, right? So now we get that 3D volume. We take that, we have to compute the sensitivities. So now we take that, we compute the sensitivities. Okay. And then the next step is we're going to invert the IP data using that mapping function. So that's the third step. And so that's what we're seeing. So we now have a 3D volume of chargeability. We can take a look at that next time. So we're slicing through. And there's the end result. So what we see here is there's this high chargeability that is extending from here and coming in through here. There's something else here, and there's a few other things. This is a very complicated area. I mean, this is real geologic area, right? But we see something that's coming in here, and this is coinciding with that moderately high conductor back there. And this is, in fact, the Mount Noblet horizon. So this is the guy that's really interesting. So if we do an interpretation here, so here we have the this region of high conductivity, but not absolute high. That's coinciding with this, and then if we follow the high chargeability along, it kind of comes in like this. So this is the Mount Noblet horizon. That's the one that is mineralized. In addition to that, there's a few other things that are chargeable. Oh, well, first of all, let me make one comment here. We said that the black shale unit should not be chargeable. Okay, and here's the line for the black shale. Okay, coming through here, and if we look through virtually all of this, okay, there's no chargeability. There is one area here that there is chargeable material, but that is not connected with the black shale. When we were in Australia, we were talking to people about this, and they said, yeah, there are still people who are working on this particular project, and they said, yeah, you know, we've recognized this for some time, that there is something chargeable out there, but they're not sure what it is, and they might actually go back and drill it just to see what's there. So that was kind of interesting. But anyway, here's the success story, right? DC resistivity outlines the major conductor, kind of highlights this, but the big diagnostic physical property is chargeability, and we got that. So I think that's, yeah. There's two things that are connected with IP that I think would be of interest here. Certainly when I was talking to Terry, he was saying that one of the big issues for Chile, for mineral exploration, is EM decoupling. And I think we're at a point where we could profitably talk about that. And then the other thing I'd like to talk about is airborne IP, but in conjunction with looking at multi-parameters. So I think both of those things would be very much of interest. And they're still setting up, so just can't quite figure out whether to. let me just set the scene just for a few minutes, and then maybe we'll kind of come back. But first of all, there's sort of EM IP that I want to talk about. So generally, we take a transmitter, we turn it on, right, and then we turn it off, and there's information that's at the early times. In an IP experiment, you'd be measuring sort of at later times, and information at early times is often discarded. Just like, oh, okay, that's EM coupling kind of stuff. I'm just going to try to get rid of it. So the real curve when you turn this thing off looks like as follows. Immediately after turn off, you get an EM signal. So there's going to be a negative that's coming in, and then the IP kicks in, and then you have something positive that is decaying. So the signal that you measure, if you're able to measure this really rapidly in time after turn off, would have the following three phases. There's first of all a DC resistivity, and then you turn it off, and then you've got an EM, sort of an EM response, and then you've got a region where there's both EM and IP, and at late time, now we have this decay, so that's your IP signal. Generally, most contractors, they're just interested, okay, let's do the DC, and then let's do the IP. So let's just start measuring late enough in time so that we're just capturing the IP signal. Or if we're measuring up in here, we have to do something to get rid of that EM response. So there's two things that come into play. One is the potential for using this very early time data as a time domain EM signal, and the other is in regions where they're overlapping, how to separate them out. So here's kind of a better diagram for that. So this is in the off time. Okay. So you've turned things off. So we're going to be looking at sort of what is happening right in here. So we're going to be looking at the off time. At the very early off time, it's almost all EM induction. You can't see any. These signals are so big that any IP effect is completely swamped, and all you're seeing is EM induction. At very late times, all you're seeing is the IP effect. But there's a region in the middle here in which things are confused. So it's sort of a kind of intermediate region. So if in this zone here, you wanted to try to recover the IP data, then you somehow have to get rid of any EM signal. And this is what we're going to do. We're going to take an observation in here, and we're going to compute what the EM response would be, which means we need to know the conductivity. And then we can subtract that, take the observation, subtract the EM, and then we're just left with IP. So that's a way of doing it, and we have a couple of options in general. So we're going to estimate what the EM response would be for this. So that means we need to know the electrical conductivity. Okay, how do we get the electrical conductivity? Well, we could do it from the DC part, right? So if we took the DC values, invert the DC values for conductivity, might be okay, and then do a 3D forward modeling to calculate the EM response from that conductivity, and then we subtract that from the observations. That would be the IP. Option one. Option two is like, wait a minute, why don't we treat this as a time domain EM experiment, right? So I got the transmitter on, I turn it off, I measure some responses, So I could actually use this part in here as my signal and do a time domain EM inversion to recover the conductivity. Use that conductivity to calculate my forward EM response, subtract that from the observations, and end up with an IP signal. So I'm just going to show you how that works at this point. So we're going to do a gradient array. So here's here's one electrode here, A electrode, B electrode. So the current is actually going around that loop like this. And then we've got some objects here. This A1 is very conductive. A2 is moderately conductive. A3 is neutral, it's the same as the background, and A4 is resistive. So I got big conductor, smaller conductor, no conductor, and a resistor. Okay. Now those blocks are also going to be chargeable. The two blocks that are going to be chargeable are, what happened? Oh, so these are the cross sections. The two blocks that are going to be chargeable are A2 and A3. So these two guys here are chargeable with both with 0.1, and they both have the same kind of time decay. So if I look at the DC data, so that's the DC data here, and I look at the DC voltages, I get something that looks like that. If I transform them to apparent conductivities, I get a high conductivity, apparent conductivity here and here. So remember, those were the two big conductivities. So I'm clearly getting some information about that. If I look at the off-time data, then depending upon what time channel I'm going, I've got different different images. So here's 5, 80, 130. So those induction effects are kind of moving through this whole signal. At late time, I see that these two objects here are shining out. Remember, those were the two chargeable bodies. So let's suppose I do the DC inversion. So I take the DC data, and now I'm going to invert those. And here's my recovered model. So this is in plan view, that's in cross section. So we see we do not a bad job of recovering the highest conductivity. That's an intermediate, and that's a resistor. It's not bad. In order to do that inversion, because we only have a gradient survey here, we actually have to put a depth weighting into the inversion. The same as in gravity or magnetics, you have to do a depth weighting. So that was incorporated in here. If I look at the very early time EM data, so now I'm going to use multiple channels of time domain EM data in those centers. Then what I'm going to see is, or what I recover, are these two conductive blocks and that resistor. So actually, this is a better image of the conductivity than what I had before. So that's a very important issue to make right at this time, because what we're seeing here is that, oh, and I forgot to mention, there's no depth weighting in here, but I've got 6 time channels of data. I'm inverting all of those in 3D. So the fact that I have multiple time channels means I'm sensing the Earth a bit differently, because you remember yesterday when we were looking at early times, the currents are up here, later times the currents are there. So I am getting some depth information by recording things as a function of time. And I can take that, invert that, and I can get a 3D model without doing any other hocus pocus of depth weighting. And these are the results I get, and they are better than what I would have had with the DC inversion. So the information that we're traditionally throwing away is in fact very valuable. And I think one of the big take-home things here is that we should, in all of these surveys, be recording sampling very finely so that we have very early time data, use those early time data as part of our data set for inversion. And so now if we compare the conductivity models, here's the true, here's the DC, and here's the here's the EM. This is actually a closer representation. It's not bad, but it's closer. So I think probably that's a good place to leave this. And now what we're going to do is to look at the EM decoupling procedure. So the first sketch was to get an electrical conductivity. We showed that we could do it, with the DC, but we needed to do a little bit of, juggling around, at least with this particular kind of array, with a gradient array. If you did the EM straight away, you might get a better conductivity up. So that's the first step. Now we'll have a lunch or a break, and then we'll come back, and then we'll use this conductivity to actually do the EM decoupling, and then see how that works. Okay. Let's go. You can get out. Yeah.
Really? Oh, I would be really interested in that. Oh, McGill.
¿Hasta dónde llega? Nada, nada. El modelo de la inversión que... Ya, la cosa es que cuando el pico apaga, hay un flujo electromagnético que va por de corriente de todas negativas. Si no lo ven, después, y después la curva de la negativa está en el cero, es corriente negativa, y después se recupera y después decae, que es el IP. Cuando decae es el IP. Entonces, ¿y qué pasa si analizamos esa data? En vez del DC, analizamos la data del M.
Ah, y esa es la inversión.
Okay. Yeah, that'd be great. So I'm seeing your Max. And then you're working for Okay, so for what purpose did you want to take?
Right now,
Go up to your issue.
And
reduce some nitrogen. Boundaries.
So are you using? So has that been successful? Yeah, yeah.
Still for the architects.
So it's mostly, so Max, so Max. So you're trying to look at, these are both DC and So are you using
Okay.
so here's where
Oh, this sounds really
Yo creo que puede que tenga un poquito antes, porque como va a ser como final, como situación en este caso.
I thought you were
Igual te va
Okay.
¿Dónde tenían su oficina? Era en el León.
So I think there's certain
No se teníamos
Were you planning to talk a bit about that too, or actually ask?
Ya, okay. Me imagino que era mi
Yo le presto el curso de yo por acá, porque ya estaba en pero yo pensé que se
There might actually be something.
viendo o hay que hacerle otra cosa. A mí ya me complica las dos veces.
Oh, that was, I would say, also really, yeah. Yeah.
Mi mamá trabaja, pero
You had another, you mentioned another problem just before you talked about the that was awesome. We definitely have that. That sounds great. Okay, I couldn't remember watching it. Sorry? No. Yes. We got anything, so. Yeah, just finishing up. Very much and then
Santiago,
No, but I like food. Yeah. Yeah. Argentina, Chile, is next. Well, I guess we have real Oh, that's tough. I think you gotta find another driver. It's substitute off. Sacrifices at one day. And how long ago was that? They're aging well. Well, you gotta be very busy if you have find time to open the bottle of wine. I mean, I thought I was busy. There's no comparison. Just put everybody in a closer fence and let the dogs chase the kids and the kids chase the dogs, and then you can just hang out. You can open the bottle of wine. There you go.
Getting classes.
Okay, I go
Voluntarios para la reducción de emisiones con
Okay, guys.
Okay.
Okay.
Pero pensé que viera.
Parece dificultad.
How are you today?
We did try, but
Esperan que sea automatizado. Bueno, lo que se pueda.
ahí no dijo nada.
Ah, pues vale, lo dijo, bueno.
Yeah, sure, that's the one.
No, 21. Primero 21, creo 20.
Do you want extra water?
Actually, maybe I could. Hi, Daniel.
En un mundo integrado de
Whoa, that's a lot of cookies. I'm impressed. Whoa. I'm gonna take a picture of the front. Okay. Okay, I just want to flash through these again, so we'll just kind of regroup on where we are. So first of all, has everybody signed this? Because there's if you haven't put your name or your email. Okay, so our idea was that after you turn the current off, then there's an EM response, and then later on there's an IP response. And so the question is, okay, these data are generally thrown away, maybe we should keep them. And that was codified in this example here as, so this is now log scale, and the very early times are purely EM. The late times are purely IP, and then there's this region in the middle that's confused. What we're going to do is to use this relationship here, that the observation that we measure is the EM part plus an IP signal. Okay? And that means that we could get the IP signal by subtracting the EM component from the observations. Good. So now we just need to get an EM component. That means we need to get a three-dimensional estimate of the electrical conductivity. And then we put that into Maxwell's forward Maxwell solver, predict what the EM responses are, and then subtract that from the observations. The first part of that is to get the electromagnetic conductivity. And our example was this. We've got four bodies. This is very conductive, that's less conductive, that's neutral, and that's resistive. And then two bodies are also chargeable, so A2 and A3. If we looked at the DC data, apparent conductivities look like this, so that was the higher conductor, that's the lower. If we looked at the off-time data in the time domain, you notice that at the very early times, things are just completely confused here. This is really the induction from the wire that's coming through. So remember the where's the wire? Here. So we got this wire here. So we turn that off, and now we've got a lot of EM induction from this wire that comes through. So that's what we did yesterday for that grounded source. And that's going to slip through here, and it's going to interact with these with these bodies. So we not only have the DC component, we've got an EM induction component. And yeah, so at 5 milliseconds, it looks like that. At late times, that response is this is just purely IP, right? So this body was chargeable, that body is chargeable. At earlier times, though, we see kind of different types of things. At 80 milliseconds, for instance, it looks like there's something up in here. If you interpreted that as an IP response, you'd be drilling this target and it wouldn't be correct. And also you have this tendency to think this is the big kid on the block as far as chargeability compared to that. So that's what would happen if you happen to just try to make an interpretation from those signs. So now we need to get a conductivity. So we're going to, first of all, do the DC resistivity. So we use the DC values. But because this is a gradient array, so we're just measuring like the electric fields along this grid. It's a gradient array, so we only have one source. So you really do not have depth of penetration with a single source. It's like a potential field. So the only way you can make some advance is to introduce a depth weighting, the same as you do in gravity or magnetics. However, if you work with the early time channels and invert those in 3D, you actually get out a very nice conductivity model. So there's not there's no muss, no fuss here. There's no additional weighting. You just invert those data. And just to compare, this is where we ended up. What the conductivities were from the DC, you ended up with this. For the EM, you actually do better. So now let's look at the EM decoupling process. So let's concentrate at 80 milliseconds. So our IP data are going to be the observations minus the EM. So we take the EM conductivity that we had, we do a 3D forward modeling on that, and that's the predicted EM data. So here's the observations, here's the predicted EM responses. Now let's subtract those and get decoupled data. So look at this. This is, we've greatly altered this. Here's the observation. If you were thinking that 80 milliseconds was late enough that you could start to interpret IP, you'd have said, okay, this is the target here. There's the biggest targets down here, and maybe a smaller one there, right? By removing that EM part, you end up with something that looks like that. And those were the two bodies that were chargeable. If you do that for, so the purpose of this slide is to show you that, okay, we're going to use IP data as observations minus the EM response, but then the question is, okay, what do we use for conductivity? If I just guessed at a half space, I'd end up with this as a result, so that's not good enough. If I use the DC resistivity, which is not a bad conductivity model, I end up with this. If I use the EM, I kind of clean up that artifact there, and I've got a bit better response. So as far as the quality of conductivity model that you need to get rid of that EM coupling response, the DC.G does a pretty good job, but the EM in this case was actually a little bit better. If you do the IP inversion, the true IP data, so this is now in a isosurface. The true IP data volumes look like this. If you use the half space, then you've got this artificial one here, so that's purely fabric. If we use the DC, you get something like this. There's still a little bit there. And if we use the EM, kind of comes out like that. So both the DC and the EM conductivity are both pretty good. But as I said, the fact that you ordinarily throw away those early time data, they could be really useful. I want to quickly take you through a case history that our group has worked on for, probably 2 or 3 years. We just published a sequence of 3 papers in geophysics exploration or interpretation. And what we're concentrating on here is look to see, for a kimberlite exploration, how much information can you really get from from airborne surveys. So we're going to look at a variety of data, but I'm going to concentrate on the EM decoupling and the use of airborne IP. I'm not sure how many of you know about kimberlites, but this is a kimberlite pipe. This would be connected with extrusion of diamonds. Diamonds are stable at great depths, sort of 120 kilometers, and then you can get these eruptions that these pipes come up right from that upper mantle and get up right to surface, and they carry the diamonds up with them, and the diamonds are stable once they get to the surface here. This is what the things often look like. They're kind of an explosive pipe, kind of look a bit tooth-like, and they've got various acronyms here. There's HK, VK, PK. Those are all different types of kimberlite. And the one that's important to us is this PKU. It's a pyroclastic kimberlite. That's actually the guy who contains most of the diamonds. Because this is an explosive event, stuff goes blasting out, and then so you get sediments around the outside, and then things kind of fall in, but there's still a little bit of a depression, so that fills up with a lake. So characteristically, what one looks for are lakes, and then the lake bottoms are usually highly conductive. It's sediments there. So visually a lake, highly conductive, perhaps associated with sediments, and from a magnetic perspective, they often turn out to have a magnetic signature. So electromagnetically, well, first of all, this is the area. It's Cho. We'll just shorten it to TKC. It's sitting up here. So here's British Columbia, so Vancouver's down here. Next province over is Alberta and Saskatchewan. TKC is up here in what's called the Northwest Territories in Canada. There was a DIGHEM survey. So a DIGHEM is a frequency domain EM system. So it's like the Resolve system. In fact, it's an older Resolve. And Q, quadrature, okay, 7,200 hertz. So now you're familiar with all these things. This is the vertical component of the magnetic field. And you see that there's 2 conductivity anomalies. There's one here, it's called DO18, and there's one here called DO27. So those are 2 pipes. There was quite a bit of EM data that were flown, and it has an interesting history. So the first was a frequency domain EM. The second was, so that was 1992. Then they developed the airborne time domain EM. And the first one was an Aerotem, and it was flown in about 2003. So what we're looking at here is an early time channel. And contrary, so that the blue, the dark blue here, is actually negative, and the reds are positive. Now, this is a coincident, well, it's a kind of like a coincident loop system. You got a transmitter and you got a receiver on the inside. And the fact that you have a negative value indicates that there must be something that's chargeable. So this was a very famous paper put together by Peter Weidelt, I mentioned his name the other day, that showed that the only way that you could get a negative result from a transient sounding in a coincident loop system is if you had chargeability. Okay? If you look at the decay curves at DO27, here, one of the points, this is time. At very early times, it's positive, and then it decays away. So this is a log-log plot, so and then it switches. So the dashed lines indicate negative values. So it starts positive, then switches and goes negative, and then decays. So that's telling you something, that at a particular time out here, the IP signal is actually large compared to the EM. The DO18 is even more problematic. At the very earliest time channel here, these values are negative. When those data were first flown and those data were shown, people were looking at these guys and saying, we have no idea what could be. I mean, maybe the instrument's not working. Why is there not even, the first channel positive? So they went back, they fixed up the instrument, made and flew a new one. Actually, this is the one that the second one that was flown, and all that gave even cleaner data. So there was no question that those negatives were there and that they were repeatable. And in 2004, you got another system, the VTEM system, that came around and basically got the same kind of map. So this is signal. And it shows that there must be something there that's chargeable. And then some surface work using what's called nanotem also reproduced that same thing. Okay, so that's kind of a snapshot of the history of frequency and time domain EM. Initial discovery based partly on frequency, and then subsequent information from the airborne time. So now what we want to do is somehow make better use of our time domain signals, and especially trying to understand sort of what's going on in this intermediate region where you clearly have IP effects as well as you have EM reduction effects. So the first step is we've got to get a conductivity model out. Well, that wasn't a trivial slam dunk by any stretch of the imagination. So here's the result from the DigEm inversion. Or sorry, here's the data from the DigEm data suite at 7200. And then here is the VTEM data, but only those data that are positive. Because we're not going to be able to invert coincident loop time domain data if they're negative, right? Because we're on the wrong physics. But the data that are positive are given by here. So what was done is to take these data, so there's a lot of soundings in here, invert those in 3D, and cooperatively invert the frequency domain data. So kind of go back and forth and use the inversion of one as the starting model for the other, and then iterate until we finally got a model that was in reasonable agreement with both data sets. Anyway, that was a major work. There's a whole paper that's written on that. The bottom line for us is that there's a 3D conductivity model that's there. DO27, DO18. This one's more conductive than this. And the cross section is like this. So DO18 almost looks like that conductive region goes right to the surface. DO27 seems to be at depth. So let's do the decoupling. At 130 microseconds, here's the observed. We take that previous, so this is going to be the VTEM data now, right? So it's 130 microseconds. We take that 3D conductivity, forward model it, and we get this as a response. And now we subtract this from that, and we get this. So all of this signal that we have in here, that's basically EM response. All of this signal that we have in here is pretty much the IP response. So we forward model, we get this as predicted data, and we invert, or do that subtraction, and we end up with something like this. So there's a big negative here, A1. There's a little one here, A2, and kind of A3. So that's at 130 microseconds. A little bit later, we're going to have a different story. So a little bit later, it actually looks like this. So now we've got kind of a bit more strength here, and we still see something there. If we do that predicted EM data, we get this. And now watch what happens when we subtract. We get that. So what do we see? We've got a great big negative region up here, which is indicative chargeable material. And we've got this huge negative in here. So this is a real big chargeable chunk of material, which is just simply, not particularly obvious at this stage. So here's a case then where we've got a 3D conductivity model, forward model that, subtracted that from the data, and these would now be the decoupled data. So we've got that chargeability data, and now we want to invert that. That is no small feat. This work has been done by the other co-presenter for the disk, Sagi Kang. Just published a couple of papers about this. But the whole aspect of, remember we were talking in DC, resistivity about an applied electric field and how the charges would build up, right? And then gradually asymptote. So that was our idea. So if you're a chargeable material, right, the moment I turn that current on, there's now there's electric field, and gradually those polarization charges build up until they asymptote. Good to go. You have a steady state field that's a forcing function. Now think about what happens in a time domain experiment where you've got a transmitter and you turn it on. Then initially, at aerial, the electric field, there's nothing really that's coming from that, but then it gradually builds up, okay? So then there'll be a maximum, and then it will fall off. So while that field is building up, now you can imagine the same physical process that's going on. Those charges are trying to get there, but the forcing field is never uniform constant. It's kind of go, and so it's just the only time the charges have to build up is as long as that electric field is going. So you have to take account of that in this problem, and each person in here would feel the electric field at a different time. So we have to keep track of the waveform of the electric field at each pixel and look at that as the waveform for generating the charge buildup. So you can start to imagine now you've got 3D and you've got a source that at each time the electric field history is going to be different. And that means that the amount of charge that you get to be built up is different. So that seems like a pretty challenging problem. Okay, now multiply that by the fact that we've got many transmitters. Okay, so we have to do that then for each transmitter. And then you've got to couple everything together so that I find something on average that is an intrinsic chargeability. This is a very challenging problem, and Sagi is getting his PhD. He's going to defend in a couple of weeks about this. But this is, I believe, the first time, I think this is the first time that airborne IP data have been extracted and inverted in 3D. So, a geophysical first here. So we take that inversion at 130 microseconds. So we take the data, we invert that, and look what we see. So here's A1. So that's at DO18. So there's something really chargeable there, and here, and here. So A1, A2, A3. In cross section, it looks like that. If we do the same at a later time, at 410 microseconds, look how everything has changed. What we've seen up here is getting smaller amplitude, and A4 down here is getting immense. So this is now this is shining up as a big chargeable object. And here's the cross section. So things are changing as a function of time, big way, and we're able to unravel those by actually doing 3D inversions of these airborne data. What we might be interested in is how we can recover some in. So these guys here that we're seeing, these are all kind of pseudo chargeabilities. This is kind of like an effective value at chargeability at a particular time. If we try to represent what the frequency dependence is of electrical conductivity, here's one way of doing it. It's called a Cole model. It can be written either in terms of conductivity or resistivity. So an earth rock is parameterized by the following constant. First of all, a conductivity at infinite frequency, so that means that there's no chargeability effect. The intrinsic chargeability eta, which went from 0 to 1. A time constant tau, which is related to how quickly things decay, and a frequency dependency. So there's 4 parameters. What has been done up to this point is that each time channel has been inverted to get a 3D volume of pseudo chargeability. Okay. Now what we're going to do is take. So again, we use aerial as an example. So at early time, if we do an inversion, you have some value of chargeability. At later time, it's different. Later time, it's different. Right? So now we take those 10 values that we just have, because we inverted 10 time channels, and we look to see, okay, what kind of chargeability curve are we generating from this? That is effectively related to this. And so now we're going to take those numbers and do a parametric inversion to find some of these parameters. Okay, so we've got chargeabilities as a function of time, and we want to convert those to a parametric representation that looks like that. So if we look at A1 up here, and we take some pixels at A1, so there's a region up here. So let's take maybe 8 or 9 pixels that are right in the center, and we invert those on chargeability and tau. We're going to fix C in this case. So we're going to look for chargeability and tau. Then we get these purple guys here. So these are the estimates of chargeability and a time constant. If we look at A2, we get the yellows, A3, we get the reds, and A4, the greens, we get up here. So there's a huge difference between what's happening out here for A4, which is this guy here, compared to the other guys. So there is definitely two different kinds of rocks there. They have two different kinds of time constants. So this has got a time constant of 10 to the minus 10 cubes, sorry. So 1,000 microseconds. This has got more like 100 microseconds. So more than an order of magnitude difference in the rate at which the polarization charges decay back. So that means, okay, we're talking a different material between this guy and any of these. Okay, so we now have a bit of a like a classification thing here. So now we come to data integration. So we've got the gravity data, the magnetics, frequency domain, time domain, and we want to kind of put all of that together. So we invert each of these in 3D. So we get a 3D density model, 3D magnetic susceptibility model, we get a 3D conductivity, and we have some chargeability, some chargeability models at different times. So there's like an early time and a late time. So these are the results that we get. So that's density, susceptibility, conductivity, early chargeability, late chargeability. So we could regard those as 5 different physical properties, and we could try to make a geophysical rock model, right? So take something that's got, okay, low density, high susceptibility, high conductivity, low early time chargeability, and high late time chargeability. That would be one combination. Or we could do other things too. So you put them into a statistical classification algorithm and come up with a number of kind of distinct combinations and units. When we do that, we get basically, well, we get a background and then 5 rock units. And these are color-coded in terms of red, blue, green, yellow. And the rock units look like that. Okay? So there's our geophysical rock model. We don't know what names to ascribe them, but those are geophysical rocks. If you put a drill hole through these, then you'd be able to recognize, ideally, that, okay, the green corresponds to a VK unit, and this corresponds to some other unit or whatever. In fact, there have been a lot of drill holes that were done. This area has been thoroughly drilled. None of that information was used in this. But subsequently, we compared the geologic rock model, okay, that was generated with all those drill holes, to the geophysical rock model. And there's actually a really kind of nice correspondence between these two. So that's really pretty exciting. That means that there's the potential for taking multi-parameter geophysical data, generating rock models that are geophysical, and trying to then tie them, into the geology. And of course, once you've got a little bit of this, then these inversions are all done blind. There's no real a priori information about the existence of anything there. They're just each one done independently, and definitely if it was a mature project, you could start to think about taking constraints, information from here, using its constraints in there, and whatever. So that's it. I want to close here pretty soon. I do want to show you one thing, because I think this will be important, and maybe not tomorrow, but it'll eventually be important, and it's probably something to make sure that we at least touch. And it has to do with induced polarization over landfills. I mentioned this a little bit yesterday. Here's a map of Tucson, Arizona. It's in the southern United States. And the little purple region in here is the city limits in the 1950s. The dark region out here encompassing the light blue are the current city limits. The stars here indicate places where garbage has been dumped. Right? So initially, here's the initial city limits in 1950s. So you're in a city, you got garbage, let's go out a kilometer or something like that, drive away, dump the stuff. And then gradually you end up building up over top, and then you've got all kinds of, because there's toxic leachates, there's mercury, arsenic, cadmium, lead, all the stuff that you don't really want to have. It gets into your drinking water, it causes problems. Landfills are also a real construction hazard. And as I said yesterday, it can also devalue your property. If you happen to have bought something, a piece of land, and now somebody finds like, wait a minute, that's over top of a waste dump, your land's not worth very much. So that means you need to locate the landfills. You may need to assess their size. You may need to clean them up, dig them up, and reclaim things. The thing I want to mention, these are the kinds of things that are typically in a waste dump. There's a lot of electronic and technological stuff, construction debris, earth materials, green waste. So that electronics, it could be metallic objects, heavy metal solution. Construction debris is kind of like, cement, iron, wood, wallboard, asbestos, glass, plastics. Earth materials, clays, various kinds of fill, and green waste, trees, wood clippings. So those are the things that you might characteristically find in a waste dump. And then the question is, what are the physical properties? Well, the resistivity could potentially be diagnostic, but sometimes you don't even know whether it should be resistive or conductive. Right? So the resistivity might be very high for wood or wallboard or stuff like this, or plastics. But it actually could be really low for metallic objects. So kind of depending upon what's there, the resistivity could be high, low, variable. The chargeability that's associated with this kind of is also somewhat variable, but each of these materials could potentially be chargeable. So you get, waste dumps with metallic objects in it. It's likely chargeable. Construction debris, earth materials, definitely clays, and maybe even green waste. So I just want to show you kind of what's traditionally done. So traditionally you use magnetics. So the reason for magnetics is that, especially if you've got electronic equipment, anything that's got iron or steel in is going to give something. So construction debris, especially if it's got rebar in, is going to be susceptible. So magnetic susceptibility might work. So this was done. Sometimes you do magnetic susceptibility, sometimes DC resistivity. Here you're looking for resistivity. And then also you could have a time domain system or a frequency domain system. Those are your EM components. But if you look at some of the results that come from doing DC and IP experiments, so here's the resistivity, and here's the historical boundaries of the waste dump. And there's not a huge correlation. On the other hand, chargeability looks like this. So the chargeability has been a good indicator. That's a mixed solid waste, and it seems to be kind of correlated with the historical limits of that waste dump. If you look at a different area, the western pit, now this has construction debris, and here's the historical boundaries. So this is now really resistive, like the wallboard, stuff like that. So that's that. But if you look at the IP, then again, there's a pretty good indicator there. Here's another landfill. I like this example, and we also have another whole case history on this, because this often happens. You're trying to get rid of your waste. Where do you do it? You want to put it in a hole. Where do you have a hole? Well, let's suppose you've got a valley of some sort. So you just drive the truck up to the end of the valley, dump it off, and off you go. But gradually, the valley fills up, eventually it's the edge moves out there. With the passage of time, water percolates through here, and dissolved metal ions, leachate can come out the bottom. And what we're looking at here, the red is the conductivity. So there's regions of high conductivity in here, and there's also regions of high conductivity in here. Okay. What we're interested in is both of those things. We're interested in the waste dump itself, because that's probably the stuff that needs to get cleared up. We're interested also in any leachate that's coming off, because that's going to contaminate your water. So the conductivity tells us a lot. If we now look at the IP part, the contours are for the IP signature, and you can see they're all concentrated up in here. So that the interpretation of the, okay, this is waste. This is the waste dump stuff, okay? And in fact, that corresponds pretty responsibly with the historical boundaries of this site. And this red stuff coming over there, that's your leachate. So that combination of DC and IP, in this case, is very informative. And as I said, the case history that we have in here, I'm not going to go through, expands on that. Interesting enough, even organic waste seems to have some weak IP, which was kind of news to us. And yeah, there's some places that, like this is classic, right? So here we do a DC experiment, and we got conductive stuff here. The IP is like that. So the fingerprints are matching. That's probably a good indicator of exactly where that stuff is. This is an interesting case because it has to do with monitoring. So initially, in 2003, there was an IP survey that was done, and this was the IP signature that was obtained. Then the place had to be remediated. So I'm not sure what they did, but they did all, both air sparging, and I think they were pumping in fluids or something too. Anyway, they did a 4-year bioremediation program. And then in 2009, they repeated the survey, and there's a huge difference here. So not sure whether this would work all the time, but here's one example where it appears that before, when all of the material is there, you get sort of a high value of IP response, and then as time goes on, after you've done the air sparging or whatever, you've reduced that response, and so that might be an indication of just how well you're actually doing in your remediation program. So again, if that works, then this is kind of like a nice geophysical tool that can supplement spot drill hole measurements. So in summary, I just want to say that resistivity is useful, but it's you sometimes don't know which way it should go, whether it should be resistive or conductive. But IP just might be a more reliable indicator, and certainly using the two of them, probably much better off. So if you're going to do DC over a waste dump, make sure you also do the IP. So this is actually a really nice case history that welcome to. Okay, time to wrap it up, and then we'll go for lunch. I just want to talk, I want to kind of summarize a little bit where we were and just talk a bit about the future. So let's kind of talk about what we've covered. Well, we did BC resistivity, and again, as I said this morning, kind of recasting the resistivity problem in terms of charges, I think is hugely, hugely beneficial. And then we looked at the DC resistivity for Mount Isa. Talked about the EM fundamentals. I hope that you now see this curve, this response function here, and it's going to be completely, you're just completely comfortable with it. As well as remember the other photo or picture that we had with respect to the currents that the small 2-coil app for the frequency domain, where you see the secondary currents, and you divide that into like an in phase and a quadrature phase. That with this completely tells you what's going on. So those are the two kind of iconic things. In time domain, we did a water example looking at the paleochannels, and the aspect there that was really, I think, intriguing and shows where geophysics is going to go. It's not in getting the conductivity structure itself. I mean, that was useful, helped determine what the depth of those paleochannels are. But also in then combining that with drill hole measurements and getting a 3D geologic or hydrogeologic conductivity model. And then that allowed them to do some pumping tests so that you could decide, okay, if I'm pumping water out of here, or maybe I'm injecting it, then you can find out where the water is going from, whether wells are connected, all of those things. Buchpernong. Oh, just a second. I can't decide if I'm going to sneeze or not. I think I'm not. Okay. There we go. Sorry. Buchpernong, there was an area that irrigation area up here, a lot of salts coming in, and the Murray River. I forgot to tell you this. So we've been doing this case study. We inverted both the SkyTem data and the Resolve data. And so we've been really interacting with these data sets, and we've kind of seen these pictures of the Murray River. So Lindsay and I were in Adelaide, and we were on our way to Brisbane for this disc. And so we were getting on the plane. I asked the steward attendant, I said, is there any chance that we'd be flying over the Murray River? And she said, oh, sure. In 15 minutes, we're going to fly over it. And so I said, wow, this is great. So we'll just kind of keep our eye open. So we're partway through, like just 10 minutes up in the air, and all of a sudden it's the captain who comes on over the PA system. And he says, and for all those Canadians out there who are interested in seeing the Murray River, take a look on the left. And there it was, and it looked exactly like this. It was just... yeah, it was just picture perfect. It's just out of our wings. So that was kind of cool. So that was frequency. So that's kind of looking at salt water. So any kind of saltwater intrusion problem or something like that, that works. They're actually going to use that for monitoring. We did grounded sources. We actually spent a lot of time kind of thinking about grounded sources. We kind of went through the details, right? And tried to make you think about, okay, what's happening? Where are the currents, right? I turn the current off. What's going to happen in the ground? Well, I'm going to get a current in the ground that's just the same as the wire, and then that's going to diffuse out. That's a really important concept to have in the back of your mind. And then we had these grounded currents. But you kind of get the idea that if I ever have a current filament in the ground, and if I let it go, it just kind of swishes outward. And then if I have, in doing that, if I have a wire snaking around someplace. So here's clearly where the path of that wire, current wire on the surface of the earth, makes a huge difference, because that's your transmitter. And when you turn that off, there's going to be that image current, and then that's going to diffuse away through. So those are really important concepts to have at the back of your mind. And we had a number of examples of this. So the one was in India, where using that to find the thickness of the sediments. And the low-chem data showed that the sediments actually thinned towards the bottom compared to what they thought before. We didn't really talk about hydrocarbon de-risking, but we did talk about the general procedure for finding hydrocarbons at sea, and we realized, like, okay, this is a resistor. So my first shot is that I'm going to use something that's related to like a DC resistivity problem, and then I'm going to drive currents through there. I'm going to get charges build up, and that's going to be my signal. And that led to the following kind of geometry, that we have an electric dipole here. But if we want to have something that's 2 kilometers, want to see something that's 2 kilometers deep, then we better have our receivers line that's 6 or 8 kilometers long. So that was the hydrocarbon de-risking. And I also showed you that movie. So the movie and was designed to help understand what the signals are going to be, because you can actually look at the wave fronts. And by watching a time domain sequence in the wave fronts, you just see what's happening, just the same as in the GPR when we did that, right? So that was the thing there. Marine, CSEM, yeah, we actually talked a little bit about, didn't talk about methane hydrates. We then went to natural sources. So then we looked at magnetotellurics, case history with respect to geothermal systems, and then applied that to Chilean example, Santa Cecilia, for mineral exploration. And that was a kind of a triumvirate, because there was DC resistivity. So for shallow, there was CSAMT, provided shallow, and then wanted to do something deeper, so the MT went there. There was also a few images of IP, which we hadn't covered then, but if you went back now and you looked at the IP signature, you'd see something different. The Z-temp, which makes use of natural sources, but we have a towed array for the vertical magnetic field. We did a synthetic example and a field example for mineral exploration. GPR, we went through the basics of GPR, showed you some of the wave fronts and how things decay. We looked at the application for self-driving cars, which was just kind of interesting. And then for GPR, a lot of applications for geotechnical engineering and near-surface stuff. If you're trying to find small voids in roads or things like that, tow a GPR system over, and that'll help you out. And we went to induced polarization. So we explained the IP phenomena and showed how we could go ahead and invert for IP data. That was a 2-stage process. You do the DC resistivity inversion first, and then you calculate the sensitivity, and then go ahead and invert that. And we applied that to Mount Isa, and that was really the diagnostic thing, because then we found this. A large problem in Chile, talking to Terry, saying that one of the, still one of the big challenges with inverting IP data here in Chile is that for many cases, there's really a strong EM component that's still in the data, and you need to get rid of that. So I showed an example of how one could do that. Somehow you need to get a three-dimensional conductivity, and it has to be a pretty reasonable estimate. Otherwise, you can end up throwing the baby out with the bathwater when you do the subtraction. So that was the EM decoupling, and then we applied it to an example, a synthetic example for ground-based, and an airborne example where we have taken inductive source time domain EM data and managed to invert that at each time channel and get out sort of early time and late time chargeability models, and then made a rock model out of that. So that's a lot of stuff. So what does future hold? It's not too early for that, is it? Oh, it's afternoon. Yeah, it's afternoon. We have an afternoon beer. And the good news is Daniel's buying, so it's like he's just like the nicest guy ever. You're all invited. And then we'll follow that by Pisca, some Pisca sours. We'll just bail on the whole afternoon. Okay. Okay, so this is how we started today, right? So we started. Okay, we got problems to be solved, and there's lots of them. We've got high quality data. We can invert now any of these kinds of data in 3D, and we've got web tools to communicate. So here's where the disk fits in. So where's the future? Certainly, monitoring is going to be very big. I mean, whether it's dam integrity. Here's a case in British Columbia, Mount Polly, just burst through. Slope stability, aquifers, coal seam gas, enhanced oil recovery. Any of these things can require the ability to permanently instrument areas and then just monitor what is happening as a function of time. And actually the monitoring problem and the time-lapse problem in some sense is easier than trying to find the absolute conductivity or something like that, because a lot of the places have a lot of infrastructure on, and if you're trying to find a survey that could model all of that, that could be really challenging. But if you're just looking for differences, then you could do a representative inversion of a data set prior to doing any prior to your monitoring start, and then you just use that as a basis and continue on with the monitoring. So that is that makes the monitoring problem a little bit easier in some respects than the absolute value. Here's another problem. This one is motivated by what's going on these days at the in the SDG conferences, and that is, remember I talked. Okay, so here we go. Here, so this is the guy here sitting down here that you want to find, right? So he's maybe a couple of kilometers down. Maybe this is a hydrocarbon, or maybe you're pumping in CO2, or maybe you're putting in a fracking fluid. I don't care. You're trying to find this guy. If you're sitting up at the surface and you're going to try to design a survey, remember the first thing you got to do is excite the object. Well, if I'm sitting up at the surface, then it's really kind of, imagine a DC resistivity. You've got to have big long lines, and it might actually be hard to excite this object. However, if we're able to funnel the transmitter down, so if we're able to funnel a current down here that was close here, then we might be in much better shape. So one way of doing that would be perhaps have a generator up here and put one electrode of the generator on here and basically use this as an extended current electrode. That's what people are currently excited about in the hydrocarbon industry, because they've got all of these fields, they've got all these wells out there, and maybe there's an opportunity to use those as extended electrodes. That would, imagine if you could fire a current down here, then that current's going to go through there. Just imagine all the charges that are going to be built up on there, and now you've got sensitive voltmeters up at the top that you can measure those electric fields. Okay. All right, so that's fine. So what are you up against if you were going to try to do just a model to see what you could possibly get out of that? Well, the big issue is scale. And there's two kinds of scales. There's spatial scales and there's physical property scales that are going on. So from a spatial scale, let's look what we're up against. So here's a pipe, okay? Maybe it's 10 centimeters in diameter. And so that's small. The outside or rim of the pipe, maybe that's only a centimeter thick, right? And so you've got to model things at that scale of, you know, centimeters, or actually less, because if you're going to model this pipe, then you need to have cells that are smaller than the thickness of that wall, so that now you need a fraction of a centimeter in your numerical modeling to do that. Okay, so now you got cells that are a fraction of a centimeter. And then you got to go all the way down, right? Well, you're going down, so this is actually maybe a couple of kilometers. So think about that. If you're going to try to model everything in terms of cells, you've got, you know, fractions of centimeters, and you got kilometers. So you got a lot of scales like here, and you know, so this could be, you know, hundreds of meters and tens of meters. So that's going to be challenging numerically. The other thing that's challenging is that this casing is both conductive and permeable. The electrical conductivity might be 10 to the 6 Siemens per meter, and this background is maybe 1 Siemens per meter. That's 6 orders of magnitude. Right? So if you're going to try to model that stuff numerically, it's going to be challenging. Also, the permeability could be really high. We haven't talked about permeability entering into the EM problem, but you know, that might be 50 to a couple hundred. And then in reality, you know, the pipes are maybe not pristine, they might be corroded. So like, how do you handle all of that? In cases like this, where you've got axial symmetry, the code that I was talking about yesterday, this 2D SIL code, can actually work with it. So it can do things that are conductive, permeable objects, cylindrical symmetry. So this could actually be millimeters on the side, and this can be kilometers now. And what you're seeing here is the currents that are going out the side of the pipe and emanating through the bottom. The magnitude of the currents that are going out the side of the pipe depend upon what that conductivity contrast is between here. So if you change the conductivities in that background formation, you'll change how the currents come out of the pipe. So there's lots of really interesting things that are going on, and it kind of cause you to think and to, you know, kind of have an idea of what you need to do to make progress. Another thing that is important is the infrastructure that exists in your area. So here's a typical well pad. So you're drilling down, then you're doing these horizontal wells out this way. And you might actually have to be careful. There might be a cable that's going from here to some tool shed, in which case that, you know, you think you're putting currents down here, but you're actually lighting up the tool shed inadvertently. So you need to know details. You need to know about the infrastructure. You need to know how to model things. That involves large contrasts and challenges. You got to choose the appropriate survey at any particular time. Here's an example. We've been working on this. A PhD student working on SAG-D. Maybe that's not very relevant to China, but there was a couple of people here from Venezuela, I think. Anybody from Venezuela? Perfect, 2, perfect. So you'll affiliate with this. So we've got basically oil sands here, and the way to that's used to extract it is that you drill horizontal wells, 2 of them, a few meters apart, and you put steam into the top one, and then that steam reduces the viscosity of the oil drips down and goes into the bottom pipe, and then it's extracted out. So there's a couple of different scales of survey. If you're going to set up something like this, then the first thing you'd want to know is, okay, so what is the background conductivity? And that might be done in various stages. You might have some airborne surveys, or you might have some ground surveys. There's observation wells that are mandated. So you might be able to use those, measure vertical component of electric field. And then once you've got that background conductivity, then you'd want to be able to see if you can find out where the steam is. That's always a big problem, right? You inject steam, but maybe it's preferentially coming out here, and there's maybe a little bit of a blind zone in there. So can you find those steam chambers, and can you find the blockages? Those would be really valid problems. What the thesis that Sarah devised, that she's finished up her PhD, was actually to show that instead of seismic trying images, which seismic does not do a good job, by putting up a large vertical loop, in fact, a couple of them, and using electric sensors measuring the vertical component of the electric field in boreholes that are already mandated because they need to be observation wells, we can actually get out some pretty good images. This one also might be of interest to you. If we look at the electrical conductivity cross-section, we see that the target of interest is this one at the bottom. The red guy is a cap rock. He's conductive, and the hydrocarbon formation is underneath here. What is of interest is this contact, this elevation of the top of the hydrocarbon reservoir. When we do an airborne survey over a region and invert it to get out a conductivity model, and then use that to estimate the elevation of that formation, we end up with an image that looks like this. So it's color coded as far as elevation. So blue is high elevation, or yellow is high, blue is low. Get an image that looks like that. Contrast that with what the hydrocarbon industry has done, which is namely to drill a whole bunch of wells. So each of these is a well that takes you down through to estimate what the top is, and that information is extracted and put onto this image here. So that's from the borehole data and interpolated. So you can look at this image and look at this and immediately see just the large correspondences that exist, and hence the information content that could be obtained from this. These data were probably acquired in a day, and it takes you a lot longer to punch holes in each of these black dots. Yeah, and then here was the example of, it's a synthetic, but if you had, so these are steam chambers. So these are the horizontal steam chambers, and one of them had a bit of a blockage. That's what the steam chambers look like across here in cross section. And the goal is, can you image those? So there was a surface loop and borehole receivers, and a frequency domain EM that was applied, so inverted in terms of 3D. And here's the image that's obtained. So you see that there are 3 steam chambers, and you've got a bit of an area of blockage. So the oil company that was kind of responsible for this research, or for funding part of it, was actually tremendously excited about that potential for using EM to find where the steam is. Just came from a conference, Exploration 17. It's a mineral exploration conference that's held every 10 years. And so this is number 5, I believe. And there was a lot of talk on improved instrumentation, lower noise, more power, more control on the waveform, making sure that all the filter parameters are known, everything that's connected with the system, the orientation, the positions, all of those. So that is definitely coming, as well as the way data are collected. I mean, we saw one example with the drone, but there's AUVs and ROVs, and all of that is. So here's a couple that actually go underneath. So that's an inductive source for EM on the ocean floor. So that is being used for seafloor massive sulfides at this point. So there's definitely a future there. Lots of data. I mean, these days, what we're seeing is that we need multi-component receivers, need lots of transmitters, lots of receivers. You simply cannot do 3D anything without illuminating each pixel from multiple directions, and that means you just need to have basically big data in multiple kinds. Not only geophysical data, physical properties, geochemistry, geology, and eventually maybe putting all that together with machine learning algorithms and making it advanced for it. Marine EM is definitely going to be in the future. There's gas hydrates, so yeah, well, you've got, there's inferred and recovered, so you kind of got some off here. So maybe that's a part of your future life. C4 massive sulfides, I've mentioned this a couple of times, we haven't really shown. You have these black smokers that come up, so there's lots of mineralized material that comes up and then kind of precipitates down. And that gives rise to high percentages of mineralization on the ocean floor. And really, that's a very applicable place to actually go mining. Right? So you just need to delineate where these things are. And the technology for doing that is done. Right? I mean, they can easily put machines on the ocean floor that just chunk, grind stuff up, pump it up to a ship, load it, no muss, no fuss. So you're going to see that unquestionably coming about. And that, although it's going to disturb local environments on the ocean, I mean, overall, the ecological footprint of that might be substantially less than, mining a big porphyry copper deposit. Oh, and tectonic hazards, well, you're definitely aware of those here. This is an example of actually using large-scale MT and control source EM to try to find out what the electrical anisotropy is. So we hadn't talked about anisotropy, but sometimes current in a rock can get preferentially easier to travel in one direction compared to others. And so this was a map of the anisotropy, which might have some influence about understanding how the rocks are deforming. Large scale, I showed you the picture at the beginning. So this is Australia. This is their OSLAP. They're doing magnetotellurics over the whole continent, and similarly over the United States. There's a number of reasons for doing that. One of them is just to understand what the continental structure is. Another motivation is these geomagnetic disturbances that we talked about. Remember, we had the solar flare come in? So that's a storm. That's a big geomagnetic storm. And that has the potential for causing a lot of havoc with the satellites up there, but it also could cause a lot of havoc on the Earth's surface. Because if you think about our power grids, I mean, what are they? They're just like a big loop that's going around, right? So now you've got, imagine a big time-varying magnetic field that's coming into that. And imagine the EMF that's induced in this loop. And if you get a large voltage surge in that loop, then that gives rise to additional currents, and the first thing you know, you've overridden any safety limits of your transformer, and the transformer just goes, it just pops. And that surge can propagate down that line faster than you can turn it off, and before you know what's happened, it's just like a bunch of firecrackers that have gone off in the space of a few hundred kilometers. So that actually happened in the late 1990s in the eastern seaboard of the United States and in Canada. There was a big solar storm, and it just knocked out the entire power grid for like 3 days. So they never want to have that happen again. And so now they're grounding the circuits before. I mean, some of them were grounded before. But one of the things that they need to know in order to understand what to do, you actually need to know the electrical conductivity of the Earth so that they can predict what the electric fields are going to, so have a storm, what are the electric fields going to be at this particular point, so how much do I need to guard against? That means you need to know that conductivity. So that's a motivation. A lot of people at the USGS are devoted to those geomagnetic hazards. Water, huge, huge issue. Finding it, delineating it, monitoring the aquifers, managing saltwater intrusion, pollutants, all of these. Dispersive properties. We talked a little bit about IP, but I think that's just we're just seeing the tip of the iceberg at this point, as far as the use. So there's been a lot of work on trying to use this for characterizing rocks, especially for mineral exploration. But there's large potential for ice, water, permafrost, bioremediation. Measuring hydraulic permeability is something that people have been working on for a long time. Basically, look at the imaginary part of the complex conductivity, and there is a relationship to hydraulic permeability. So if you could find that, and if that could be reliably estimated, that would be huge. For permeability, the effect of it, certainly in soils, the fact that there's a viscous remnant magnetization, or that magnetic permeability is frequency dependent, that is a very common problem for unexploded ordnance research. There's not many groups that seem to be, or countries that seem to be really interested in this. We've got a whole bunch of stuff on UXO, but if you've got a little bit of magnetic material in your soils, the electromagnetic response can behave very differently. Instead of falling off as t to the minus 3 halves, it actually falls, or t to the minus 5 halves, dBdt, it'll actually fall off as t to the minus 1. And that amplitude can greatly just swamp the signal. So if you're working close to the ground, it's called superparamagnetic effects, to SPM, if you've seen that term. If you're working close to the ground, that can be a real issue. And there's also the potential for bioremediation, because if you have a bug, some kind of bacteria that's going in and he's chewing up and ingesting things, and then the trick is to put magnetite out, but it's kind of different grain sizes, and then that gives you this SPM effect. So there might be applications there, but I think again here it's an area where that it's coming. I mean, there's things to be done. As the instruments get better, then you can start to see these second order effects, and once you can see them and reliably estimate them, then you can start to do things with it. So that will happen. And I showed you this data integration, multiphysics, different physical properties, get rock models, and modeling and inversion. Again, things are just exploding, right? With cloud computing, high performance computers everywhere, collaborative developments and open source. I mean, these are things that we're just on the cusp. We're just now really starting to see the effect of. This afternoon, talk about SIMPEG. Lindsay will take you through what we have there. And then there's also other groups that are developing basically Python-based simulators and inversions. And, so we get a community that's going and, connecting through GitHub for version control and making sure that everything really is open access and properly taken care of. Modeling and inversion. I think you might see Lindsay, Soggy, and myself and another day coming down here. I think one of the things that would be really useful is to kind of combine some of the things that we've been talking today, but really get into the numerical modeling and inversion, and kind of working with that. There's a couple of things that we've concentrated on with respect to interactive computing, and that is visualizations. Like, here's Maxwell's equations. They're great. I mean, what can you say? They code up everything that you kind of need to know, as well as the boundary conditions, but they're not intuitive. It's at too high a level. It's too general to really extract meaningful information. So you gotta pick questions or pick ideas one at a time, and then maybe you can make an app. And then by translating these equations into currents and charges and images, then you start to see what happens. And as I said before, the way to use these apps is to recognize their ability, first ask a question, try to decide what you're going to see, and then press a button and see what you get. Again, I want to stress future collaboration. I think that's where the field will grow. We can no longer afford, as a geophysical community, in particular as an EM community, to try to do everything in isolation. It's so inconvenient. It's such a waste of time. Rediscovering wheel after rediscovering wheel after rediscovering wheel. Just can't afford to do that. So you need to collaborate, take advantage of the skills that you have, but take also advantage of the skills that somebody else has, interact, work together. The the 7th step for case histories is a great way to interact, believe me. If I can force somebody to put their problem into this framework, I can easily grasp where they are, and then it's really easy to communicate. If you send me a 40-page booklet of stuff, it's too much stuff to get through and you can't figure it out. But parsing it down into something that's really simple is good. And there's lots of potential here for future collaboration because we're always looking for case histories. We don't want any case history. We want a case history that really makes an impact, something that really shows something, shows how a technique can work to solve a particular problem, so that a non-specialist can pick this case history up and say, oh my God, why I should be using this, right? Or particularly other things, things that are just really challenging, like you just cannot figure it out. There's been a couple of cases here where it was Mike Webb was talking about a case where they've got a big conductive overburden, big conductor underneath. They weren't able to see through it with MT for some reason, which I don't know. But they were able to see it with time domain EM. So that's interesting. And the question is okay, why is that, right? And it just doesn't seem to be quite right, or there's something to be understood there. And so the question is, okay, what's happening? So somehow making those kinds of problems available then gives something to sink your teeth into, as far as okay, let's try to understand that. And then that could also be, a case history as to, understanding the fundamentals. Why doesn't this particular technique work in this case when, in principle, you kind of think it should? Right. So, and if those things were then made widely available so that everybody could see it, then the whole level of knowledge rises up. So that collaboration, editing on GitHub, I just can't stress how important that can be for making it easier for each individual to achieve his goal, but to elevate the field as a whole. So yeah, that was basically it. What were our goals? Want to inspire you, show you a different variety of potential applications, illustrate the effectiveness through case histories. Seeing how something actually works in practice is very effective. Build a foundation. I still can't stress this enough. A lot of people kind of poo-poo this course or what we're trying to do, say, oh, well, fundamentals, I took a course one time, right? Like, I know all that stuff. But people don't know all that stuff. Even people who think they know a lot of that stuff sometimes don't know all that stuff. And if you really, really are grounded in the fundamentals, then you don't make mistakes about choosing a wrong kind of survey, or maybe end up spending lots of money on something that you should have realized, like, wow, that's a bit suspicious. I don't think that should work. So this business of exploring and visualization with apps and our open source resource, again, Lindsay's going to talk more about that. Set realistic expectations. You now know, even just by looking at the images of those currents, okay, everything is diffuse. So you're not going to be able to get good resolution at depths with EM, right? You look at the latest times, say, okay, well, I'm seeing down to that deep, but where's the currents? Well, they're all over the place. So there's no hope that you're going to be able to see 10-meter thick reservoir at 2 kilometers down. And I keep stressing this, development of a community. That's really where we got to go. Got to kind of work together, contribute, open source stuff, and capture case histories. So here's our resources. As I said, Lindsay's going to talk about each of these this afternoon, but here's our basic site. It's GeoSci.xyz. We got GPG. That's Geophysics for Practicing Geoscientists. This is a site that we basically use as a text for our undergraduate work for our geological engineers, the geologists, and even the first-year geophysicists who don't know anything. And then here's our EM GeoSci, SimPay, the DIS case histories. And we've got lots of apps. You've seen one, you've only seen one, but you've seen that there are others. So again, Lindsay will show you more on how to access those, what to do with them, kind of what they look like. And lastly, I don't know whether you appreciate it or not, but this has been a monumental effort to put this material together. And there's no way a single person could have done it. There's no way a single person and even 2 really great co-presenters, Lindsay and Sagi, could have put all of this material together. It comes from a team. All these guys are part of my group at UBC, but there's other people that have contributed here too. And we've been working on this material for probably a couple of years now, and it's been totally absorbing our lives. We're kind of where we are. But that's the GIF DISC team. And well, you're not going to join us tomorrow because tomorrow is today, but this afternoon, we're going to hear from you about your case. How many people are prepared to give a short talk? 2, 3. Wow, it's 7 yesterday. Now we're down to 3. Okay. Anyway, so we'll do that right after lunch. And that's it. Thank you. So there is an evaluation form, right? So before we go for lunch, I'd like you to fill out an evaluation form, and then she'll go for lunch.
En su caso es la web.